I am honored to have this academic exchange on optimization issues with everyone. My name is Li Chenran, and I'm from Dalian Maritime University in Dalian, China. Today, I will share my research on the fully parametric design and optimization of counter-routing rim-driven thrusters. Today's content includes three parts. First, the research background and objectives. Second, the numerical simulation methods and the numerical validation. And third, the optimization design and result analysis. First, let's take a look at the background introduction of the Shaftless RDT. The traditional propeller modeling method uses a point-line surface approach. The propeller model is fixed and cannot be modified, with each section unable to be smoothly adjusted simultaneously. Optimization requires a complete redesign. In this paper, the parametric design method for propellers uses a varied design parameters to express its feature line, allowing the program to generate the propeller model with a single click. By modifying any design parameter, the propeller model can be smoothly transferred freely. The 2D profile configuration to 3D radial distribution can be edited and designed, providing a predictive model for execute performance-driven design. The contra-routing shaftless rim-driven thruster proposed in this paper combines the feature of RDT and contra-routing propellers. Similar to the RDT, the motor stator is placed inside in the duct for propulsion. The shaftless structure effectively reduces the generation of hot vortices, which plays a significant role in reducing hydrodynamic noise and improving propeller efficiency. However, due to the unique structure shape of the counter-routing RDT, its modeling method is particularly complex. To accurately represent the counter-routing RDT, the paper explores a set of parametric express methods suitable for the blades of the counter-routing RDT, thus achieving fast and accurate modeling of the counter-routing RDT. Next, let's take a look at the numerical simulation methods and the numerical validation. The counter-routing RDT is a 3D solid formed by stretching and routing the airfoil profile in space. Typically, the radial distribution of parameters at various profiles represents the entire counter-routing RDT. The design variables for the counter-routing RDT blades manually express and locate the blade profiles. The chord length, max thickness, and max camber describe the shape of the airfoil profile. Rake, scale, and pitch accurately represent the circumferential, axial, and radial distribution of the counter-routing RDT blade profiles. To accurately fit the main parameters at different radial positions of the counter-routing RDT into parametric curves using a minimal number of control variables, the paper employs the F-spline curve fitting method of the parametric modeling of the thrusters. The process begins by plotting parametric curves from described points and at different radial positions. The different points at both the beginning and the end of the radial positions are selected as the reference points for the fitting curve. The main radial parameters are fitting use F-spline curves, as shown in this figure, with fitting errors all within 0.5%. The figure illustrates how variations in F-spline curves based on the initial airfoil cause changes in the airfoil shapes due to the alteration in the 2D feature parameters. Since the counter-rotating RDT is a new type of special thrusters, its blades differ from conventional propellers. Therefore, its model needs to be redefined and redesigned. The KA470 content pitch propeller is used as the last one, with modifications such that the root section airfoil is a wing shape and the tip section airfoil is an arch shape. The child length radial, pitch radial, and other parameters remain unchanged. Only the max thickness distribution along the radial is altered, creating the blades for the counter-rotating RDT. The figure shows the mapping relationship between the characteristic parameter curves and the throttle. Each parameter curve of the rotor selects three design variables: the y value of the curve's starting point, the area enclosed by the curve, and the coordinate x, the y value of the curve's endpoint, with no real and the scale, totaling 12 design variables. The purpose of establishing a fully parametric thrusters model is to express the characteristic of the thruster in a relatively simple way, to establish the relationship between the geometrical parameters of the thruster and its performance. Since the counter-rotating RDT is a new type of thruster, there is no experimental data domestically and internationally. However, the ducted propeller and counter-rotating RDT share structural similarities. The number 19A duct has been widely used on ducted propellers, and its performance have been validated in practice. The internal structure of the counter-rotating RDT is similar to that of the ducted propeller. So the number 19A duct will be used as the last one for modification, and the optimization based on the will yield the geometrical model of the counter-rotating RDT. Therefore, this paper used the KA470 series propeller for the Netherlands ship model basin for hydrodynamic validation. The match selected in this paper consists of 3.2 million elements, and the overall efficiency deviates from the experimental values by less than 5%, indicating that the results calculated using the match are reliable. At the second International Conference on Underwear Propulsion, the 11th SMP held in Hamburg, Germany, the controlled pitch propeller VP1304 was used as a case study. Non-uniform in floor or oblique floor conditions were simulated by tilting the propeller shaft by 12 degrees. The conference provided the geometrical phase data of propeller, forming the basis of comparative analysis between calculation and experiments. Therefore, the paper uses the propeller to conduct numerical validation of pressure precision with and without cavitation. This paper calculates the pulsating pressure results at monitoring points on the cavitation tuner for the propeller in oblique floor conditions, both with and without cavitation. The section compares the pulsation pressure detection results at point P2 obtained from the above setting with the experimental values of case 3 provided at the 15 SMP conference. The figure shows that regardless of whether cativation occurs, the pulsating pressure amplitude as the first blade frequency is significantly higher than that the second frequency. Comparison analysis with the experimental data released at the 15 SMP conference shows that the calculation results have a small error. further proving the rationality of numerical simulation method and match division method used in this paper. Similarly, the paper performs match division for the counter-routing RDT. The routing domain is divided using a card-seal match and the prism layer match, while the stationary domain uses a cut-seal match. The total number of match elements is 5.6 million. For these calculations, the routed speed is set to 10 RPS. Finally, let's take a look at the optimization design and result analysis. The paper tests the convergence of various algorithms and finds the MOSA algorithm have the fastest convergence speed. Therefore, the paper uses the MOSA algorithm for optimization. By selecting and setting the range of the design variables for the counter-routing RDT, a multi-objective optimization system is established to optimize the hydrodynamic performance and pulsating pressure performance of the counter-routing RDT. Based on the so-called algorithm, the MOSA algorithm is used for multi-objective optimization for pulsating pressure performance and hydrodynamic performance. The optimization design goals are the open water efficiency and average amplitude of pulsating pressure in the 0 to 1000 Hz range. With the structure of the counter-routing RDT as the constraint, the configuration parameters of the counter-routing RDT are the optimization design variables. By comparing the pressure maps before and after optimization, it can be seen that the optimized counter-routing RDT has smoother blade structure. The middle and the root part of the rear blades are wider compared to the original prototype, resulting in a more uniform pressure distribution on the blade surface. Therefore, the optimized counter-routing RDT exhibits superior hydrodynamic performance. A sensitivity analysis was conducted on the relationship between each variable and the objective function and the design variables with stronger dependence. We selected to further adjust the optimization range. As shown in the figure, the flow field at the blade plane of the optimized propeller is more uniform, and the area of high velocity region has increased. Additionally, the open water performance of the optimized propeller is superior to that of the original prototype propeller across various advanced configurations. Therefore, the hydrodynamic performance of the optimized shaftless RDT is better. Monitoring points are established as actual and radial position for the counter-routing RDT. As shown in this figure, the actual and after points are positioned at 1D, 2D, and 3D. By comparison, it can be seen that the optimized RDT has a smaller pulsating than the original prototype structure, indicating that the optimized RDT exhibits superior performance. As the distance increases, the amplitude of the pulsating pressure at the monitoring point decreases. The optimized counter-routing RDT has lower pulsating pressure amplitudes at the first blade frequency at both actual and radial monitoring points compared to the original prototype structure. This paper uses a two-step method to extract the continuous broadband spectrum. First, the upper envelope curve of the original structure is calculated based on the structure to obtain the local maximum values of the fracture amplitude. Then the local maximum values are processed using the averaging weighting method, and the envelope curve is mostly to remove random variable, resulting in the pulsating pressure spectrum. Finally, this paper forecasts the turning performance of the exciting Shaftless RDT. It is found that with a rudder angle of 15 degrees, the counter-rotating Shaftless RDT exhibits superior turning performance. Given the complex geometrical configuration of special thrusters, this paper establishes a parametric expression system for counter-rotating RDT. Enabling multi-objective optimization design of the geometrical configuration and performance of thrusters on the different design parameters. The research findings are as follows. This paper integrates the geometrical reconstruction technology, hydrodynamic performance evaluation technology, and optimization technology of the counter-rotating RDT. By using the characteristic curve parameters in the fully parametric configuration of the counter-rotating RDT as optimization design variables. An optimization design system based on multi-objective optimization framework is constructed. The optimization results show that on specific design parameter combines the hydrodynamic performance and proceeding pressure performance of the thruster as superior to those of traditional breeds. The open-world efficiency had improved by 5% compared to the pre-optimization state. The performance-driven configuration design approach provided valuable technical guidance for the design optimization of new thrusters. That concludes my presentation. Thank you.